Hi everyone, I'm Marcelo from ReviewPad, and I just want to say a few words about the meetup before I give the stage to our guest today. So DevTools Porto, not DevOps. DevTools Porto is a small meetup that we do every month to talk about tools for developers. We ourselves are building a tool and just trying to get up to speed with the next generation of tools that are coming up and try to level up. You can find more information about the meetup. We promote through basically ReviewPad because it doesn't make sense to start fragmenting things. So either on Twitter or Discord, or even check out the previous talks from YouTube. And today's talk will also be live streamed and then it will be uploaded for on GitHub. So today we have Bruno from Datadog. So super excited for starting the year learning about streaming and events, I would imagine, with Kafka and I suppose a little bit of Java perhaps. So a little bit of Java and so thank you so much, Bruno, for coming today. And at the end we'll have some beers and some time to chat. And if you have, people, or if you want to talk about something that you find interesting about this space, feel free to reach us, and we'll make sure to talk about that. Thank you so much.
Thank you. Okay, so hello, my name is Bruno. I decided to do this talk on stateful streaming with Kafka. This is a talk I wished I had the opportunity to see some years ago. And before I start, let me thank you guys for joining us here and to ReviewPad to inviting me and organizing this. It's pretty cool, thank you. So a little bit about me. I joined Mindera, a company founded in Porto some years ago. I'm a biomedical engineer, but I've been a software engineer all my career. Then during the pandemic, I started working as a freelancer through TopTal. And currently I'm working in one of the security products from Datadog. So during this talk, I will explain some basic Kafka concepts that I think are critical to understand what I'm going to talk about later. And so I will mention record, topic, partition. I will mention segments and the cleanup policies from Kafka, and also explain what a consumer group is. And then I will start explaining what stateful streaming is, making a comparison against what stateless streaming is. I will explain what is the purpose of the state in stateful streaming, and also explain how a stateful streaming can be fault tolerant and recover from crashes. Then I will explain what the Kafka Streams API is, and I will do a live demo with some code that will probably wrap everything up, and it will be much easier to understand what I mentioned before. So what is Kafka? This is a screenshot from Kafka website, and they define Apache Kafka as an open source distributed event streaming platform. And event streaming is basically the capability of, in real time, gathering events from multiple sources, either mobile devices, databases, software applications, sensors, etc., and storing them durably and reliably, and making them available to be consumed either in real time or at any point in time in the future. And Kafka allows you to do that. So you can write events to Kafka, you can consume events to Kafka, and you can store them as long as you want. So a message on Kafka is divided in 4 different parts that you can initialize when you write something. So they have a timestamp and some headers, just like an HTTP request. But most importantly, and I will talk about them a lot in this talk, they have a key and a value. Each message is then written to a topic, and the topic it's just a way of organizing your messages. Let's say you can have like a payments topic, and only payments data will go through that topic. And the topic is divided in partitions. And the partitions is a way for you to scale your consumers and be able to process more data in parallel. When you produce something to a Kafka topic, you write directly to a specific partition. And the partition from which you will write to is decided based on the key by default. You can customize this behavior, but by default, the same key will end up in the same partition. So in this example, you can see that if I send a message with key 1, they both end up in the same partition, so partition 1. And for example, key 2 will end up in partition 2. Since you will have more keys than partitions, of course, the same partition can be shared by different keys. As you can see, the key 3 also ended up in partition 1. Then a partition is also divided in segments, and segments are just files in which the messages are stored. And there's only one active segment at a time, which is the latest one. They have incremental IDs, so the latest one is the one in which you are writing messages, and messages are always appended to the end of the file. A new segment is rolled, so it's created based either on size or time or both. So let's say that each segment is 1 GB. When we reach that size, we generate a new one, or we generate a new segment every 30 minutes, or both, whatever comes first. Then the way for us to clean up this topic, since we don't want to store data forever, is through cleanup policies, and there are two. There is delete and compact, and these cleanup policies will be quite important to understand a concept about the Kafka streams later. So a delete cleanup policy is basically we delete entire segments. When a new segment is inactive, so in this case the red one, we are not writing messages to it, Kafka checks the timestamp of the last message in that file, which is the youngest one. And if it's older than a certain threshold, it knows it's safe to delete the entire segment, so it deletes everything. On the other hand, we have the compact cleanup policy, in which Kafka will delete old messages, but will always keep the last message for a specific key. So for instance, if my segment has 3 messages, all of them have key 1, but one of them is green, the other one is blue, and the other one is orange. After the compact runs, only the orange one will be stored, and we will successfully delete 2 messages. So a consumer group, another Kafka concept, is the way for us to define consumers, and now we will consume and process messages. By definition, each consumer group will consume from a topic, and a consumer group will see all the messages from all the partitions once. So this means that if a consumer group, in this example, have 2 different consumers, so 2 different instances of the same application running, each one of them will consume only one partition. So consumer 1 consumes partition 1 and 3, and consumer 2 will consume partition 2 and other partition. So in this example, you don't see like partition 1 being consumed by both consumer 1 and consumer 2. So if I scale up these consumers and I put a consumer 3 in this case, maybe consumer 1 will stop consuming from partition 1, and that partition can be assigned to the new consumer. So basically, as I said, this is the way for you to scale the consumers, but it doesn't make sense to have more consumers than partitions. So we are limited by the number of partitions on your topic. Now, that's enough for Kafka concepts. Let's go straight into streaming and a comparison between stateless and stateful. As the name implies, stateful streaming is the streaming in which messages can be processed independently, and they don't depend on previous events. For instance, if I have like a stream of logs and I want to generate a notification every time I see an error log, that doesn't depend on previous messages. I just see an error, I emit a notification. And this type of streaming is very easy to scale because I only depend on the number of consumers I have, and I don't have any kind of state. On the other hand, if I have a stateful streaming, I need the result of previous processing to be able to process my message. Let's say that I have a stream of words, and I want to count how many times I've seen that word. So whenever I consume a message, that processing depends on the previous result, on the previous count. So I'm able to increment that count. For that, I need some kind of state, either stored on a database or in memory, but I need to have a state. And this, because of the state, is very hard to scale. So this diagram, I hope you can see it fine, is a very generic example of a stateful streaming application, except the topic, which is a Kafka concept, but everything else is very generic. So we have events going through a topic, and then I have my application and my consumer. and it has some piece of code that's processing that message, and it also has a state. And you can look at this state as an in-memory hash map with like by key and a value, and I keep it in memory, and every time I receive a new event, I go to that hash map to get the last state. Whenever I consume these events, I can also produce different kinds of outputs. It can be a log, I can write something to a database, I can emit other message to other Kafka topics, I can generate notifications, whatever I want. Okay, let's see now an example. Let's say that I want to count words of events, and my event will look like this. So my key will be a word, in this case, potato, and the value will be 1, which is the count I want to increment. When I start this application, so this is the very first message I'm consuming, my state is empty, so it doesn't have anything. So when I look it up on the state, there is no data for potato. So I know that I need to initialize that state, and basically I need to store in the state that the count for that word is 1. And then I can log the result of that processing. On the other end, if I consume a second message that looks exactly like the first one, when I go to the state that time, I already have something there, which is potato 1. So then I need to increment the count, store potato 2, and I log potato 2. I think this is pretty simple, but what happens is if my application crashes, I lose this state if it's in memory. So I need some kind of persistent storage that lives outside my application. So whenever my application restarts or crashes, or I deploy a new version of it, before I start consuming events, I need to restore this state on the application. So I'm able to process the events and get the same result I'm expecting. So for this, we can use Kafka Streams library, which is a client library. It's written in Java, and it's used to build applications and microservices. It will allow you to consume and then manipulate, aggregate, join your data. And if you want, it will also allow you to write results to other Kafka topics. But of course, during the processing, you can also write to databases, generate notifications, and so on. It's designed to be simple and lightweight, even though I could argue with the simple a little bit. It provides fault-tolerant local state, and for the persistent state storage, so for this part that I was talking about, it will use other Kafka topics to basically back up this state. And I will be able to show this during the demo. So for the local state, instead of using an in-memory hash map, because usually the size of the data we are trying to process doesn't fit in memory, it will use RocksDB, which is a Facebook key value database that writes data to disk, and usually disk is plenty available in our application, and it's cheap, much cheaper than RAM. So it will use RocksDB at the local state, and Kafka Streams will allow you to do stateless and stateful operations, and I will focus on these ones during my demo. There's one limitation. I wouldn't say it's a big limitation, but it's one, which is the Kafka Streams library will only allow you to talk at a time with a single Kafka cluster, which might not be a big problem, but if you want to investigate this or use it, it's a limitation to consider. Now, let's talk about two concepts of Kafka Streams. And I don't think this will make much sense now as I'm talking about them, but maybe in the demo, it will be easier to understand. And if you want, I can go back to this slide later. Basically, these two concepts are two classes in the library. One is the KStream, and the other one is the KTable. You can look at the KStream as just a stream. If you're familiar with Java, it's just like a Java stream. You can do stateless operations on it, like filter and map, just a very basic stream of data. And as an example, would be like events, log events. So you'll just have like each event has one line of logs from your application. It has a status, a timestamp, etc. So the size of the stream, since it's backed by Kafka topic, will increase over time. So it makes sense to use a delete cleanup policy to clean up these topics. So as size keeps growing, we just delete old data. A KTable, it's another concept. I would say it's quite hard initially to understand. It also uses a Kafka topic to generate this KTable, and you can take a look at it as an abstraction of a changelog stream. And it will be very similar to a key value database, So in these topics, we will have one record per key, and we are only interested in the last value for that key. Let's say that I add a topic, and every time a user edited his profile in my website, I will generate a new message for this topic. So it would look something like I have a key of with my user ID, and the value would be the name and the email. If a user changes his email, I generate a new message to that topic. So I have the same user ID in that topic again, in the same partition, but this time the email is different on the value. I'm only interested in this last value because the other one is outdated. Because of that, it makes more sense to use the compact cleanup policy. Also, you can consume this data and put this data in a key value database, right? Because since I'm only interested in the last value per key, I can basically generate a table out of this. Let's take a look at an example because I think this is a bit abstract. Let's say that I have a topic, it's empty when I create it, and I have my state or my KTable, it's empty in this case. When I get the first message, it has key 1 and value orange. I will put that value in my state. Then I get another message, different key and different value. I will store that value as well in my state. But when I get a third message, it has the same key as the first one. And so I will override what was on the state, and I will put a new value, which is green. If we wanted at any point to restore this state, I don't need to consume the first message. So I can basically mark it to delete. I can use the compact cleanup policy, and when Kafka runs this policy, it will delete this message. So to restore this state, I will only consume 2 messages and not the entire topic. This is very useful when you have like a lot of repeated keys in your topics. To restore the state, you can consume much less messages. Okay, now let's take a look at 2 very specific methods that you can do both with K-streams and K-tables. The first one is a K-stream aggregate, which is basically the example I gave with the word count. So per key, I will generate a new value, which will be stored on the state. And in this case, the state would be the word and the count. But this can get much more complex. My value can be a very big object. The other thing, and this is a bit more tricky, is instead of the state being generated by my messages, I can generate the state out of another Kafka topic. Let's say that I had the same topic with keys as words and a value as an int, but this time I had another topic and I call it translations topic. In this translations topic, I would have messages with the same key as the original topic, so same words, but the value would be the translation of each word. In this case, potato translates to batata in Portuguese. I would create a KTable, so a state, just like this one, of this topic. So in here, I would have potato and batata as the value. And that would generate my state. If I restore my state before starting consuming messages, everything is in there. So when I consume the first message, in this case, the word potato, I would look it up on the state, I would get back the value, and I would be able to log the translation. Okay, one thing that's very important to understand for this to work, both these topics, the topic and the translations topic, need to have the same number of partitions. If they don't, the keys will end up in different partitions, so I'm not able to join them successfully. And also, another thing that Kafka Streams does is that it will ensure that if I'm consuming if this specific instance of my consumer is consuming from partition zero, for the original topic, it will also consume from partition 0 on the other topic. So we are sure that the state will be totally filled with the data we are expecting, because if the translations topic partition 0 was being consumed by a different application, like the keys that are there in that state would be from a different partition from the original topic. And if we join data, we would get basically null. Okay, now let's go into the demo and some code. And this is what the demo will look like. And in this example, let's imagine that we work for Spotify or any music streaming application. And we have a songs topic. And the songs topic is just a topic in which we write all of the songs we have. We have the songs by song ID and the value as an artist and a song name. From this topic, I can generate a table, so a key value database of ID, and then the artist and the song name. At the same time, we have another topic, which is the streams topic. So every time a user listens to a new song, we emit a new message with a random ID. So just stream ID, say UID, it's totally random. And the value is song ID and user ID. And we need to create a pipeline using Kafka Streams that will join this data, repartition this data, and in the end, we want a summary of which songs each user listened to and how many times. So the first thing is to create a KTable out of this topic, out of the songs topic. Then we will need to join this data from the KTable with this data, but they don't use the same key. One uses song ID, and the other one is just a random ID. So we'll do something that's called a repartition, which is write the same data, but choosing a different key, so we are able to join the data. And it makes total sense to use song ID as the new ID. Now I have this ID matching this one, I'm able to do a join, as I said. And the result of this join will be an enriched streams case stream, keyed by song ID as well, but the value will have more data. So it will have song ID, user ID, artist name, and song name. Then we'll do another repartition on this stream by user ID, but the value is the same. So we just change the key. We write to a different topic, and we just change the key, not the value. At this point, I'm able to do an aggregate, so an operation very similar to the word count I mentioned. And when I get the first message for a single user, I will have only one song there. So in this case, AC/DC Thunderstruck. You listen to it once. And when I get a second message for that user, I'm able to add to the state another song with count one as well. If a third message has a repeated song, I will be able to increment the count instead of adding it to the map. So let's take a look at how this would look like. So this is, I don't know if I still have time. Yeah, cool, thank you. So this is AKHQ. So it's just a user interface to take a look at data in Kafka. You see that I have the two topics I mentioned about. So we have the songs one, I already populated it with some data ahead of the talk. So I don't know, you can take a look here. I have data keyed, as I said, by song ID. So this ID is 24. You can see it matches. And my topic has two partitions in this case. And this topic also has two partitions. This is very important, as I said. And this topic is currently empty, so we're not writing data to it yet. So let me start this first. Okay, cool. Let's take a look at how the code for that entire pipeline would look like. First of all, we can create, so we will use a streams builder object from Kafka Streams, and we'll create a table from it. This table, as I said, will be created with the topics songs. This is this part on top of the pipeline. Then we will start creating a stream from the streams topic. And first, the streams topic had a random ID, so we will need to select a new key for this streams topic. And this new key will be the song ID, as I said. And because of this, because we changed the key, we are now able to join this stream of data with a new key with the songs KTable, which is also stored by song ID. And the result of this join is just, sorry, wrong object, is just an enriched stream, as I mentioned, which will have all of the data. So song ID, user ID, song name, and artist. Then after we join this data, we need to repartition it again by user ID. And now we have all the data by user ID in a different topic. So we need to group it by user ID and aggregate it. So doing like the word count. And doing this aggregation will give us another object that will be written to this stream summary Kafka topic. And this aggregation will look something like this. So it's just a user ID and a map of like the name of the song and the count. Now I will start my application. I will write some streams to it as well. Okay, let's take a look. So I didn't do anything and some more topics showed up in here. First one to take a look at is this state song change log. So, sorry, I clicked on it by mistake. So this state topic changelog is used to basically rebuild the entire songs K-table. You can see that it is the same. It looks exactly the same. But when Kafka Streams created it, it already created it with the compact cleanup policy, which is very clever because I only need the last value for each song. And you can also note that no one is consuming from this. So I have no consumer group on this topic because it's only used to restore the state. It doesn't do anything during my application. You can see that it also consumed, it also could consume the same number of songs that it was in the original topic. Now, we need to repartition this topic. And so we have a new one here. And you will see that the streams that we had that were keyed, I didn't show that part, sorry. I didn't show you. So we have here the streams topic. It has a random UID as ID, and has the song ID and the user ID as value. We need to repartition this topic, and you can see that now I have a new topic with that data. So I have the same data, but now partitioned by song ID. So I'm now able to join the KTable with this topic, and I will get an enriched streams that I repartition again, but by user ID. So in the end, I have a topic that will look like this. So I have the song ID, the user ID, and then song name and artist name. So I was able to join both topics and I repartition it, but by user ID and not song ID. The last one is the aggregate part, which is this topic. And let's take a look at the specific key. Let's say user ID 7, for instance. First message we got for it was you listened to Billy Joel, the Stranger, once. And then we got another message. You listened to it twice. Oh, he really likes that song. So now 3 times. And then eventually it starts receiving more songs. So as I get streams from that user, I'm able to start adding data to this stream summary. And that was it for my demo. I have this code available in my GitHub. You can also find me on LinkedIn and some other resources here. Do you have any questions?
You have some time for questions.
Somebody wants a mic?
Which one is the UI, by the way? You need a mic, sorry.
Yes.
Hello, so first question, which one is the UI that you use?
This one.
HK, okay, cool.
It's pretty cool.
No.
And it's open source.
Yeah, nice, thank you.
Forgot to share your screen. There.
A small question. How are the topics stored? Like, are they some file in some?
Yeah. So the Kafka cluster, it will. So I can give a little bit more. I can speak a little bit more about that. So my Kafka cluster locally, it has two brokers, broker 1 and broker 2. As I mentioned, the topic is divided in partitions, and each partition will be assigned to one of the brokers as the leader, and the other ones as the follower, because I can have my partition replicated in more than one broker. And then the leader is able to store all the segments for that topic in disk, so they will be stored in a durable way. I can show you something in here. So you can see that, for instance, for this topic, songs, I have 2 partitions, 0 and 1. The leader for partition 0 is 1, but I have a replica in the broker 2 as well. So I have 1 replica of this topic. So if my broker 0 goes down, I still have the data in the other one, even if I lose the disk.
Okay. Just a follow up on your demo. Like, how do you feed the? So there's basically 2 streams, right? That you are creating. One is the songs, which you already populated in the beginning, and then there was another one which was the users.
Yep.
How do you populate? I'm kind of used to seeing this more like as a pub sub, where you basically have topics, but I guess a topic there is quite different than a topic here, where you just basically add something to a queue and then it's automatically taken out when you consume it.
Yeah, so I think it's the same. So whenever, in this case, whenever there is, whenever we change a song, like we change the name or there was a type on the artist name, we would emit a new message to this topic, it would be the same. And of course, I'm consuming from that topic to be able to update that value on the state, because I don't want an updated value there. And eventually, when the compact cleanup policy runs, it would delete the previous one with a typo. The same for streams. I just have like a Kafka producer. I'm generating the streams randomly, just writing directly to that topic. And then the case stream using that topic is consuming all of the data that I'm writing there.
Okay, thanks. Do you also have like so when you take something from the topic to consume it, if it fails, does it go back to the topic? Like, do you have like different policies for that?
Yes. So Kafka is known as a like dumb broker, smart consumer streaming platform. So Kafka, the cluster, only knows about like giving you messages that you ask it. So when you start a new consumer group, you know that you haven't consumed any message from it. And each message, I didn't mention that part, but each message has an incremental ID, which is called the offset. So it starts at 0 or 1, I'm not sure, but then it increments. And so at any point in time, you know that your consumer read, I don't know, offset 500. If that consumer goes down for some reason, it will restart and will start consuming from offset 500. So it will ask Kafka, just giving messages after that offset. But you are responsible to tell Kafka, okay, I've consumed successfully until offset 500.
Right. You're consuming one at a time, or can you consume like a burst of them, and then if it fails,
usually you can pull from Kafka more than one at a time, so in batches, but usually you process one by one.
Thanks. So does every Z stream have a change log? So each time you create a new stream, they all have a change log?
Only the ones that need a state. Okay. So the songs, it needed a state because I need to do the join. Mm-hmm. So by song ID, so I need to make a lookup by song ID. So I need a state for it. So it will create a changelog topic. The other one is the aggregate. So this stream summary. Let's say that, for instance, I was consuming this message, and I get a new message for user, in this case, user ID 2, and my application crashes. If I start consuming this message again, so a new enriched stream, and I want to add a new message, I need to have, I'm on the wrong topic, sorry. I need to have the state, the previous state, wrong one again. I need to have the previous state. So let me go back to the example. Let's say that I have this message, and the next one will also be the same song that you listen to. If my application restarts, I need to be able to have this locally to be able to increment this value. So this topic will also have a state. So it will also create a changelog, a topic for it.
Okay, but the repartition won't, because this topic already has the data that you need, basically.
Sorry, I didn't understand the question.
So the aggregation won't need a state because it will be able to recreate everything from the others.
Yes, but eventually, but you need to reconsume everything again, right?
Yeah.
Yeah, and you can see it like, so the original topic, the one with the enriched streams, it's using basically like delete cleanup policy. It grows very quickly. So maybe you are cleaning it like every hour or every day. So you are not able to generate this state from the beginning of time. And you're only interested in the last state per user, which is like the size of that, it's much smaller. So that's why you only like cache this, and you have a different topic for it, just to be able to rebuild the entire state.
Yeah.
Of course, like if you have a ton of money and you can store all your messages and you can reconsume them from the beginning of time, yeah, you would end up with the same state. But that would be expensive, and it will take very long to start your application.
Yeah, you can reduce a lot of data that way.
Yeah.
All right. I have two more. Go ahead.
Thank you. One thing that you said was that when you use the compact and delete policies,
yes,
I think you just mentioned the state from Kafka. So let's consider you need an in-memory state, so the RocksDB part. Does the compact or delete policies work there, or does the record stay on RocksDB?
Like if you never restart your application? yeah, it won't do anything. Yeah, so if you never restart your application, maybe messages are already deleted in Kafka, but they are not deleted locally. But mostly it's fine because the value that will be stored locally is the last one. So it should be good.
Okay.
If you basically restart that application, it will end up with the same state it already had before.
Okay, so it restores from Kafka and then puts it on RocksDB?
Yeah.
Okay, cool. The last one was about the, I know that you just use like simple keys or integer keys here, but does and you mentioned that, like when Kafka knows the key, it places the key on the same partition that the former one had. Does that apply like to JSON or Avro? Or?
I think it uses the hash code on your class.
Okay.
So I think if you're using a JSON serializer, probably it's consistent. If you're using anything else, maybe you need to be careful how you implement your hash code.
Okay, cool. I think that Avro does have that out of the box because it's from Apache. So yeah, but I'm not entirely sure. Maybe you would. So
yeah,
I
don't think I ever use like very complex keys.
Yeah. Okay. Thank you.
For beers. Thanks again.
Let's see.